Imagine leaving New York just after sunrise and landing in London before your coffee gets cold. Not by teleportation, not by rockets, but by an aircraft moving so fast that the atmosphere itself becomes the challenge. For decades, humanity believed there was a hard ceiling to airspeed. Supersonic flight was difficult. Hypersonic flight felt almost impossible. Not because of engines, but because physics pushes back. Air turns into heat. Heat turns into structural failure. And materials simply give up. Yet in 2026, something changed. A new generation of American hypersonic aircraft is no longer trying to cheat physics. It's learning how to work with it. This isn't about breaking records for headlines. It's about rewriting how speed itself is achieved. At hypersonic velocity, air stops behaving like air. It compresses violently against the aircraft, heating surfaces to temperatures hotter than molten lava. At Mach 5, the nose of an aircraft can exceed 3,000 degrees Fahrenheit. At those temperatures, aluminum melts instantly. Titanium weakens. Traditional jet engines fail before they even reach combustion. That's why this aircraft is not an upgraded jet. It's an entirely different machine. The core breakthrough isn't speed, it's sustained speed inside the atmosphere. Missiles briefly touch hypersonic velocity before exiting or re-entering the atmosphere. Space capsules endure extreme heat for minutes, but a hypersonic aircraft must survive that environment continuously. That single requirement changes everything. To solve it, engineers abandoned the idea of using one engine type. Instead, they built a hybrid, an engine that evolves as the aircraft accelerates. At low speeds, it behaves like a conventional jet. At supersonic speeds, it shifts airflow away from fragile turbine blades. And at hypersonic velocity, it transforms into a ram-powered combustion system, burning fuel inside compressed air moving faster than sound itself. This transition is one of the most dangerous moments in aviation. Too early, the engine starves. Too late, the system overheats. One mistake and the aircraft loses thrust at extreme speed. For decades, this transition was known as the Valley of Death. What changed? Precision. Modern computational models, real-time sensors, and AI-assisted control systems now manage airflow thousands of times per second, faster than any human could react. The aircraft doesn't fight physics, it dances on the edge of it. But propulsion alone isn't enough. The airframe itself had to evolve. Instead of traditional metals, engineers turned to advanced ceramic matrix composites and 3D printed nickel alloys. These materials don't just resist heat, they remain structurally stable under repeated thermal stress. Instead of concentrating heat at the nose or wing edges, the aircraft distributes it across the structure, preventing fatigue. This isn't brute strength, it's thermals, intelligence. And then there's the human problem. At hypersonic speed, reaction time disappears. Navigation errors multiply. Even communication latency becomes dangerous. At Mach 5, a half-second delay can move the aircraft kilometers off course. That's why this aircraft is designed to fly unmanned or optionally piloted. Autonomy doesn't replace humans, it protects the mission. Artificial intelligence manages stability, engine transitions, and thermal balance in real time, allowing human operators to focus on decision-making rather than survival. So why does this matter? Because speed changes strategy. An aircraft that can cross oceans in under an hour doesn't rely on forward bases. It doesn't wait for satellites to reposition. It doesn't give defenders time to react. Speed becomes stealth. Not invisibility, but inevitability. This is why the hypersonic race isn't about one aircraft. It's about capability. The ability to launch from a standard runway, reach distant regions in minutes, operate above traditional interception envelopes, and return without refueling or staging. That combination has never existed before. What makes this moment different from past concepts is execution speed. Instead of decade-long development cycles, this program follows rapid iteration. Build hardware, test it, break it, improve it, fly again. Prototypes are not hidden for years. They evolve publicly, step by step. each one validating real-world performance rather than theoretical models. This is why 2026 matters, not because everything becomes operational overnight, but because the hardest barriers have already fallen. Engine transitions have been proven, thermal systems validated, autonomous control demonstrated, and real aircraft have already flown. From here, progress accelerates. The next steps push towards sustained hypersonic cruise, the point where speed stops being experimental and becomes routine. And once that happens, aviation changes, forever. Commercial travel compresses continents. Reconnaissance becomes instantaneous. Response time becomes measured in minutes, not days. This doesn't eliminate other aircraft. It redefines what fast truly means. Just as jet engines replaced propellers and stealth reshaped air combat, hypersonic cruise will redraw the map of global movement. The laws of physics were never broken. They were understood, deeply, precisely, and patiently. And now speed has a new meaning.